Welcome to the G-proof, rigorous mathematical proof that God exists, using first-order predicate logic and 5 axioms that no scientist can reasonably deny. This is video 1 out of 9 videos, and we have a website at thegproof.org. Hi, I'm Mark Lawrence Donald Emerson, and I'll be your teacher. I have a BA in mathematics from UCLA. The G-proof is based on the mathematical works of many other people from ancient times all the way to the living, and I'm grateful to all of them. So, as I said, this is video 1 of 9, and this video is entitled Introduction and Overview. Does God exist or not? Well, most religious people say yes, but many Buddhists say no. Atheists say no. Agnostics say either they don't know the answer or it's impossible to know the answer. Well, obviously it depends on how we define the word God. We'll define God in a few minutes. Let me talk for a minute about what we will do in these videos. We will use pure mathematics, and I will teach you all the math you need to know. I'm a very good math teacher. The proof that God exists will be based on all of these things. First order predicate logic, 3 undefined terms about phenomena and causation, 5 axioms that we will justify, called A1 through A5, and airtight formal rigor in the entire proof. We will prove 3 theorems called T1, T2, and T3. T3 says that God exists. First we'll prove T1, then we'll use it to prove T2, and we'll use it to prove T3. Let's talk for a minute about what we won't do in these videos. We won't take any leap of faith. We won't rely on any religious scripture. We won't use any dogma. I won't do any sleight of hand. We won't use the famous ontological argument. I'm not going to explain it. You can look it up on the internet. It goes back to, I think, about the 13th or 14th century. Many famous people have worked on this argument. Our proof is completely different, and in my opinion, it is far superior. Now, is math hard for you? You know, there are huge problems in math education. A large segment of the population has been disenfranchised in math. They're afraid of math. They feel incompetent in math. But I'm a very good math teacher, and I will teach you all the math you need to know to understand the G-proof. First, I'll teach you about geometry proofs. And you know, when I teach a geometry class, every single student learns to do proofs correctly in the first week of class from day 1. That is a fact. Then I will teach you about logic proofs, and logic proofs are what we use to prove that God exists. Now, there aren't going to be any tests. This is not a class. It's just a video. But there is one test, and that test is whether you understand our rigorous proof that God exists. What do I mean by that? I mean, are you able to take this into your own intellect and go, yeah, I get it? Are you able to own it in your own consciousness and have it all make sense to you? My job as your teacher is to take you along the way and lead you to the brink where you can go, oh yeah, I get it. But it's a process. And you need to watch the videos, and we'll take this journey together. In fact, watching these videos might transform your attitude about math in a good way. Now, also, there are a lot of people who are very good at math, and you know, you're invited to come along too. All right. I have a note here for atheists. Now, I was raised as an atheist, so I've been there. I've done that. I'm very familiar with that. So, do you believe that God does not exist? Or maybe you're an agnostic and you believe it can't be known whether God exists. I have 5 questions for you. Are you intelligent? Do you respect mathematics and science? Do you possess intellectual integrity? Now, by that I mean you are unwilling to have one belief in this part of your mind and another belief over in this part of your mind where the 2 beliefs are inconsistent with each other. You don't want that. You want everything to fit together in your intellect and make sense and be consistent. That's called intellectual integrity. Do you hate hypocrisy? Do you hate it when someone stands up and preaches one thing and then turns around and practices something completely inconsistent with that? That happens in a lot of churches. It also happens in scientific communities. Are you emotionally attached to your rejection of the existence of God? Now, if these things describe you, then I have a little note, I have a little caution. Watching these videos might actually open a Pandora's box for you. Because what we're going to do is we're going to use mathematics as a window. We're going to look through the window of formal mathematics, and we're going to actually see that a phenomenon does exist that has many of the characteristics that are commonly associated with God. Now, for those who already believe in God, this proof may actually deepen your understanding of God. It did for me. If you have family members or friends or colleagues who reject the existence of God, instead of arguing with them about whether God exists, why don't you dare them to watch these videos? Argue about whether they have the courage to watch these videos. Argue about when they will watch these videos. You could offer to watch the videos with them. All right, now here I have a diagram. This is kind of a map of all 9 of the videos and all the topics that we're going to talk about and how they all connect together. And as we move our way through the videos, you're going to see this diagram over and over again, and I'm going to use different colors to show where we are, where we've been, and where we're going. So I'm going to give you a quick broad brush tour right now of all 9 of the videos. Up here on the top right-hand side of the slide, there's video 1. That's where we are right now. The G-proof, introduction and overview. Now, over on the left side of the slide here, we have videos 2, 3, 4, and 5. This is where I'm going to teach you about logic. In video 2, I'm going to give you a crash course in geometry proofs. Like I said, I'm a very good math teacher. You will understand geometry proofs, how they fit together when we finish that video. In video 3, I'll give you a crash course in sentential logic. In video 4, a crash course in predicate logic, part A. And then in video 5, predicate logic, part B. I need 2 videos for it. And because predicate logic is what we will use to prove that God exists. Then, over on the right-hand side of the slide here, videos 6, 7, and 8 will do the proof that God exists. In video 6, I'll present our undefined terms, definitions, and the first 3 axioms. And then in video 7, I'll present the last 2 axioms. I'll explain why the axioms are all justified. And I'll show that the axioms are consistent. We'll do an informal proof that God exists. And then in video 8, we'll do our formal, rigorous proof that God exists. Then lastly, in video 9 down here at the bottom right, we'll talk about the consequences. What does this all mean? Now, that's a lot of videos. Is this worth your time? The videos average about an hour each. It's about a total of about 9 hours. It's like a weekend seminar. Well, let's make a comparison here. Let's look at the time people spend searching for God. People go to churches and temples, they read religious scriptures, they spend time meditating and praying. If they go to church, let's say someone goes to church once a month, you know, it's driving and socializing, the service, all that, it's easily 3 hours. Well, 3 hours times 12 months, that's 36 hours. This is only 9 hours for a rigorous proof that God exists. Let's look at the time people spend searching against God. People read literature on atheism. People spend time searching for scientific explanations that do not involve God. There are a lot of scientists who devote their careers to this. They spend 40, 60 hours a week. Some of them do brilliant work. They're looking deeply into the whole nature of this cosmos, this creation, this magnificent universe, this solar system, this planet Earth, all the life on this planet, the miracle of all this, and they're looking for ways to understand how it works and how it came into being. But they're doing it, a lot of them are doing it with the attitude that they can do it without involving God. Also, there's a lot of time spent debunking spiritual claims. There are even journals devoted to this. And you know, this is a good thing because there are bogus spiritual claims out there. On the other hand, there are also a lot of bogus scientific claims out there, and they need to be debunked too. In any event, this is a lot of time. The videos are only 9 hours for a rigorous proof that God exists. We have a website, as I mentioned. What we're offering on the website is we have free lower bandwidth access to these videos. The screen resolution is limited. The proofs will be readable, but they'll be a little bit fuzzy. The diagrams are also a little bit fuzzy. We also have paid access to a higher bandwidth version of these videos with good, strong screen resolutions. The proofs will be clear. You can download them onto your computer, save the file. we're also offering a paid download of the PDF slides. Now, all the videos are in the same format. I'm here, I'm standing in this square over here, and over there on my left, your right, are the slides. And you can purchase a PDF file that has all the slides in it. Okay. Also on our website, we have discussion forums. Now, if you spot an error or a mistake in any of this work, please let us know. I'm human. The people who are helping me put these videos together and do this mathematical work, we're all human. We do make mistakes. If you find a mistake, please let us know. Maybe you have ideas how to advance the theory. We're actually creating an online spiritual think tank. Spiritual mathematicians and scientists are invited to join our think tank. Go to the right forum on the website to do all these things. All right. This is an outline of this video right here. Let me go over the main bullet points. First, we're going to do an informal definition of God. Then I'm going to give you an introduction to formal mathematics. And then I'm going to give you an introduction to G-theory, which is the theory that we're going to use to prove that God exists. Oh, and while I'm doing the introduction to formal mathematics, right here I'm going to give you a glimpse of videos 2 through 5. We're going to take a peek at each of those videos where I'm teaching you about logic. And then when I'm teaching you about the G-theory, this introduction, I'm actually going to do that by visiting videos 6, 7, and 8, give you a glimpse of what's happening in each of them, and that'll be the way we do the introduction. And lastly, we're going to take a glimpse at video 9, which is the consequences. Okay, so here we are back at our diagram, our map, and up at the top right here, I've made video 1 pink. So now, this is what we're going to do. And so the first thing, we're going to dive into this subtopic here, informal definition of God. Okay? All right, here we go. Here we are on the outline, informal definition of God. The first topic is godlike qualities. So what I'm going to do here, I put on the screen a list of godlike qualities, and I've divided the list into 2 parts. Section 1 of the list is the first 3, and the section 2 is the rest. Let's look at the first 3. Self-causation. Creates itself. God created itself. Number 2, omnipotence. God causes everything. Number 3, uniqueness. There is exactly one God and only one God. All right, those are the first 3. Now let's look at the rest. Goodness. God is good. Omniscience. God knows everything. God loves everyone unconditionally. God speaks to people. Divine guidance. Oh, I can hear God talking to me. Answers prayer. I say a prayer, and God answers my prayer, or maybe not. Delivers people from evil. Punishes sinners. Now, I have some question marks there. Many people believe that God punishes sinners, but many people don't. Many people who believe in God don't think that's something God does. I happen not to think so. Sits on a throne in the clouds. Well, you know, Michelangelo painted this magnificent painting on the Sistine Chapel ceiling that shows God in a big white beard up in the clouds. And, you know, I don't really think there are too many people today that believe that's what God is like, but I put it on the list anyway, just for fun. Now, etc., this is an important one, etc., because there's a lot more. What I'm trying to convey here is the distinction between the first 3 and the rest, because what we will prove is that something exists with the first 3 godlike qualities. Let's call it G for the moment, capital G. We'll prove that G is self-caused, it created itself, that it's omnipotent, it causes everything else, and that it's unique, there's one and only one. And this combination of characteristics can only belong to what is commonly considered to be God. It kind of smells like God. What about the other godlike qualities? Well, you know, it's a huge accomplishment that the first 3 have been proven. But G is not limited or restricted to the first 3 qualities. It's forward compatible. So as the theory develops, we may be able to prove that G has additional godlike qualities. We'll see. So here we are back at our outline. The next thing we're going to do is we're going to talk about uniqueness and the word the. All right, uniqueness. Unique means one of a kind. Now, sometimes we do not. Sometimes people use unique in the casual sense of, oh, it's rare or it's unusual. Oh, it's unique. We don't mean it that way. We mean one of a kind. Now, let's consider 3 properties here about operas to illustrate this. Let's look at operas by Mozart. Well, you know what? Mozart wrote 22 operas. How about operas by Beethoven? Beethoven wrote 1 opera. How about operas by Brahms? Brahms didn't write any operas. Okay, now there are 3 possibilities for equality. 2 or more things might have the quality, or exactly 1 thing might have the quality, or maybe nothing has the quality. This distinction is very important. Uniqueness happens only in the middle case, the exactly 1 case, which is why I've made it red here. So an opera by Beethoven is unique. In fact, it's Fidelio. That's the name of Beethoven's one and only opera. But uniqueness fails in the other 2 cases. There's 2 ways uniqueness can fail. It can fail either because there are 2 or more, or it can fail because there's nothing. So an opera by Mozart is not unique because you wrote 22 of them. That fails in the first way. Fails to be unique. An opera by Brahms is also not unique. It fails to be unique in the second way because Brahms didn't write any operas. Let's talk about the word the. We actually have 2 different pronunciations for this word, the and the. Now, there's a casual use of this word where we do not intend uniqueness. I'm going to the market. I'm going to the market, the market. I don't mean that the market is unique, but we have a formal way of using it where we do intend uniqueness. This is the best food I have ever eaten. And often, although not always, we switch the pronunciation to emphasize that we mean uniqueness. However, if we use the in the uniqueness sense with something that's not unique, what we will get is garbage. Let me show you, for example. We went to a magnificent performance of the opera by Mozart. What? That makes no sense. Mozart wrote 22 operas. It's not unique. And to say we went to the opera by Mozart, that's garbage. How about this one? We went to a magnificent performance of the opera by Beethoven. Well, that makes perfect sense. We went to see Fidelio. How about this one? We went to a magnificent performance of the opera by Brahms. What? That's garbage. Brahms didn't write an opera. So you see, whether something is unique or not determines whether or not it's okay or sensible to use the word the to describe it. Okay? Now we can actually make a definition. We can define words using the when something is unique. I'm going to explain the principle here, and it may be a little weird. You might go, what am I talking about? Just bear with me, because I'm going to give an example to make it clear in just a moment. Okay, so if something having a property is unique, then we can create a definition from the property. And the definition assigns a name to the unique thing having the property. Now, just bear with me, bear with me. This is a 3-step process. I'm going to list the steps, but just hang on. Step 1 is we have to prove the thing is unique. Step 2 is we put the word the in front of it. And step 3, we set the name that we're trying to define equal to that. Okay, now let me show you with an example so this will make sense. Let's talk about circles. Okay, here's a circle. Actually, I've got a circle on the slide there, but what I have here in my hand is a real circle. Okay, here's a circle, and my question is, how many times does the diameter of a circle go around? What's the diameter? The diameter, here's the center of this circle. The diameter is a straight line that goes right through the center. And the circumference is around the outside. Okay, and the question is, how many times does the diameter go around the circumference of this circle? Well, I'll tell you what, we're going to measure it. And what I have here is I have a piece of paper I've marked 1, 2, 3, and 4 on it. 0, 1, 2, 3, and 4. And now watch how I've done this. I have made it like this. So I'm going to put the 0 up here, and I'm aligning this edge of the paper right through the center of the circle there, and then you have 1 down here. So from 0 to 1, that's 1 diameter. And then from 1 to 2, there's another diameter. And then from 2 to 3, there's another diameter. Okay? And then from 3 to 4, There's another diameter. Okay, now what I'm going to do is I'm going to measure it by wrapping the paper around the circle and see how many of these diameters it takes to get all the way around the circle. All right? So now I'm going to put the 0 right here, and I'm going to keep my fingers out of the way, and I'm going to wrap this around. Okay, now you can see there's 1, and I'm going to continue around here. Careful not to drop this thing. And there's 2, and then I'm going to keep going around here, and there's 3, and then we'll get back here, and now look what's going on here. You can see we're getting back to 0 there. I'll lift this up. You can see there's 0 under there. So here's 3. So we got around to 3. We went around the circle like this. There's 1, 2, and then here's 3, and there's 0. So it's actually, the answer is 3 and a little bit more. On this circle, the diameter goes around this circle 3 times and a little bit more. That's the answer. It's a little bit more than 3. Okay? Now, what about another circle? What about circles of different sizes? Would the answer be the same on those circles? In other words, is the answer unique for all circles? Well, I think you can see that it is, and in fact, it can be proven that it is. We're not going to do that proof in here. It's beyond the scope of these videos. The answer is approximately 3.14. That's not the exact answer. The exact answer actually has many mysterious properties. Now, what we want to do is we want to give a name to the exact answer. We could call it 3.14 if that was but it's not the exact answer. It's a bad name. We need a name for the exact answer. And the name we're going to give it, we're going to give it a Greek letter, pi. We're going to name this the answer to that question, which is unique for all circles, pi. And I want to emphasize pi is not equal to 3.14, and let me just make a comment about math education here. There are a lot of students who are taught about this. They are taught, okay, they're taught that pi is equal to 3.14, and they're given a bunch of problems to do, plugging numbers into circles and figuring out their circumference and diameter, and without any understanding of what I just showed you. Pi is not equal to 3.14. All right, now, how will we define pi? We're going to define pi in 3 steps. Remember a moment ago I talked about the 3-step process? Okay, step 1 is we have to prove that there is exactly one, now look what's in red here, exactly one, quote, number of times the diameter of a circle goes around its circumference. In other words, that it's the same for all circles. Then step 2, we put the word the in front of that. See what I did here? I put the word the, and then I copied that, what was red up above, okay? The number of times the diameter of a circle goes around its circumference. That's step 2. And now step 3, I set pi, which my name is pi. I'm defining pi is the name. I've set pi equal to this phrase. And here's what it looks like. Here's the definition of pi. Pi equals the number of times the diameter of a circle goes around its circumference. And we know it's unique for all circles. But without proving uniqueness, this is garbage. Because if it's not the same for all circles, this definition would make no sense at all. Like the opera by Brahms or the opera by Mozart. Okay. So now that we've talked about uniqueness and the, now we're going to informally define God using the in the same 3-step process. Here we go. Step 1, we need to prove that there is exactly one thing that is self-causing and omnipotent. Now, we're not going to do that proof in this video. We're going to do that proof in video 8. But I'm laying the groundwork here so you can see where we're going to go with it. Okay, then step 2 is we put the word the in front of that. So we get the thing that is self-causing and omnipotent. And if we've already proven that there's exactly one, then this will make sense. And then the last step, our name, which is going to be God, we set God equal to that phrase right there. And here's how it is. Now here is our informal definition of God. God equals the phenomenon that is self-causing and omnipotent. But without proving uniqueness, this is garbage. So we have to do the proof to make the definition legitimate. And for that, we need formal mathematics. Now, here we've finished. Now, I'm making this cyan color up here on the top right, this box that says informal definition of God. The cyan color, this bright, sometimes people call it light blue, the real name is cyan. That means we're done with that. And by the time we're done with all 9 videos, everything on here is going to be that cyan color. All right, and so now what we're going to, I'm going to give you a glimpse. We're going to take a peek up here at video 9. We're going to use this in video 9. We're going to make a formal definition of God. And there it is right there. It says God equals, that candy cane sign means the thing which is self-causing and omnipotent. We'll talk about that more later. All right, the next thing we're going to do is we're going to talk about formal mathematics. All right, so introduction to formal mathematics. Here we are on our outline. This is this next section, formal mathematics. All right, what is formal mathematics? I'll tell you what it is. Formal mathematics is a system for knowing purely abstract things with absolute certainty. That's pretty neat, very powerful. And this is done by creating what we call a formal mathematical theory, and it has 3 inputs and 3 outputs, which I'll explain in a moment. In our theory, we must distinguish between terms and statements. Now, terms represent things and properties and relationships. For instance, 25, there's a term, that's a thing. Is even, well, that's a property, is a number even or not. Is divisible by, well, that's a relationship between 2 numbers. 3 is divisible, 8 is divisible by 2, that's true. 8 is divisible by 5, that's not true. Plus, that's an operation. Statements are sentences that have the property of either being true or false. For instance, every number is even. Well, that's false. Obviously, 25 is not even. Every even number is divisible by 2. That's a statement. It's true. 2, 4, 6, 8, those are all even. They are divisible by 2. 3 plus 5 equals 28. That's a statement. It's obviously false. All right, now, let's talk now about the inputs and outputs in the mathematical theory. There are 3 inputs. The first input is a logic system. The second input is a list of undefined terms. And the third input is a list of axioms. And I'm going to explain what all this means. Then there are 3 outputs. First one is a sequential list. Now note the difference. This says sequential. There are lists up here that I don't care about the order. The sequential here is very important. A sequential list of defined terms and their definitions. A sequential list of theorems and their proofs. And a system of calculation. Now I'm including the last one on here because it's part of a mathematical theory, but we don't need it. So that's, anyway, we don't need to calculate anything. All right. Now let's compare undefined terms with defined terms. Now, we need in our mathematical theory, we need terms, we need things to talk about. And we want all of our terms to be defined. It would be very nice. But there's a problem. If we try to define every term, we're going to end up going around in circles. And circular reasoning is nonsense. Let me give you a little example. When I was a kid, I had a little spelling dictionary. It was about this big, and it was about that thick. It was paper. It was not now. Today we have cell phones that have massive amounts of information in them. This was just a little paper thing. And I would look up word A, and each definition just gave one word definition. Look up word A and it would say word B. Okay, I come over here and look up word B and it says word A. In other words, it went around in a circle. That's not acceptable. We don't want any of that in a mathematical theory. Now, there's only one way to avoid that. The only way to avoid that is to accept some terms as undefined. However, the undefined terms should be things that are easy for people to grasp intuitively. For instance, if we're doing a number theory, we could use 1 and plus as undefined terms. Well, okay, what's 1? Does anybody have any trouble understanding what 1 is? How about plus? These are things that are easy for people to understand intuitively. That makes them good undefined terms. Then we use the undefined terms to create defined terms, and we have to do it in a sequential list. And each defined term has a definition. But a definition, any definition can use the undefined terms, and it can use the defined terms that are earlier on the list, but not the later ones. That prevents us from going around in circles, see? So let's give a couple of examples. We can make a definition of 2 by saying 2 is equal to 1 plus 1. Now let's look at this definition. Well, first of all, what is it using? It's using 1. It uses 1 twice. 1 is an undefined term. It also uses plus, and plus is an undefined term. Okay? Now let's take another example. The next definition in our list is a definition of 3. And we're going to define 3 as equal to 2 plus 1. This is a little different. Well, first of all, it has plus and 1 in the definition. Well, those are both undefined. But it also has 2 in the definition. And 2 is a defined term. But 2 is earlier on the list, so it's okay. See how that works? All right. Now let's compare axioms with theorems. In a mathematical theory, we want to make statements, and we want to make statements that are true. It would be nice if we could prove everything. But we're going to have a problem. We're going to end up going in circles if we try to do that. So what we do instead is we take axioms, which are statements which are assumed to be true without any proof. However, the truth of the axioms should be intuitively obvious. We want axioms where people look at them and go, well, yeah. For instance, here's a good axiom. For all numbers a and b, a plus b equals b plus a. Well, duh. The fact that it's obvious, that's why it's a good axiom. It's a good axiom because you go, yeah. All right, now let's look at theorems. Theorems are statements that are proven true, but they have to be in a sequential list, and each theorem has to have a correct proof. Now, the logic system is what governs the proof process. That's why I have to teach you about logic. The proof of a theorem can use any axiom. And it can use any theorem that's earlier on the list, but not a later one. That keeps us from going around in circles. For example, for all numbers a and b, a squared minus b squared equals a plus b times a minus b. Well, now, there's a big difference. There's a big difference between this and this. This one up here is like, well, yeah, obviously. This one is not so obvious. Now, maybe if you studied algebra, you're going to go, oh, well, that's the factoring in the difference of 2 squares. But if you haven't studied algebra, or if you're in the process of studying algebra, you need to look at that and go, wait a minute, I better check that. Okay, figure it out. Does it really work? Okay, this is a good theorem. This is not a good axiom because it's not quite so obvious. This is a beautiful axiom because it's obvious. See the difference there? All right, so now the next thing we're going to talk about in our introduction to formal mathematics is the logic system. What a logic system does is it provides a syntax, or a grammar, if you will, for making terms and sentences. And it also provides a rigorous mechanical procedure for constructing proofs and checking the correctness of proofs. And lastly, very important, it guarantees the truth of any sentence that has a correct proof, and that's called soundness. So let's talk about learning the logic system. As I've been saying, you have to understand the logic system to understand our proof that God exists. And I'm going to teach you the logic system. In video 2, I'm going to teach you geometry proofs. Not because we're going to use geometry in the God proof, we're not, but because this is the easiest way to learn about proofs. Also, this is the way proofs were done for 2,200 years, from Euclid in ancient times all the way to Frege in 1879. But there were major weaknesses and subtle flaws in this kind of proof. Then a leap happened, a historical leap happened in mathematics between 1879 and 1910 to absolute rigor. And I'm going to talk about that in this video in just a moment. In video 3, I'm going to teach you about sentential logic, which is a necessary step on the road to predicate logic, which I'm going to teach you in videos 4 and 5. Predicate logic is rigorous, magnificent perfection. Now, I'm not going to teach you enough logic in these videos for you to figure out how to do proofs on your own, but I am teaching you enough logic so you can see that our proof that God exists is correct. All right, here we are in our outline, and we're going to now look at the historic leap. The historic leap, this is a huge, huge change that happened in mathematics between 1879 and 1910. This was the birth of predicate logic. And it started with Gottlob Frege in Germany and Charles Peirce in the United States. and there were contributions by many others, and it all came to culmination in 1910 with Bertrand Russell and Alfred North Whitehead. They published a huge book together. Before this leap, mathematics was not rigorous. After the leap, absolute mathematical rigor became possible. So now, before the leap, there were many mathematical ideas that could not be written with precision. And there was no way to know for certain whether proofs were correct or not, because what proofs really were was not sufficiently understood. Mathematicians had debates about the correctness of proofs. There would be a mathematical society of meetings, meeting, and a bunch of mathematicians would gather, and one mathematician would put some proof up on the blackboard, and they would argue as to whether it was correct. And there would be factions, and some mathematicians would say, well, we think it's correct, and other mathematicians would say, well, we think it's wrong. This all changed. After the historical leap with predicate logic, the language of mathematics became powerful enough to precisely express all known mathematical ideas. And proofs became rigorous and subject to mechanical checking. They didn't have computers back in the days of Frege and Peirce, but today we do, and they're used for this. This ended the debates. There are no more debates about whether proofs are correct or not. If the proof is wrong, it's like the error is right there. Everybody goes, yeah, it's right there. Because it's mechanical. And correct proofs guarantee truth based on the truth of their inputs. Now, for 40 or 50 years, all of this stuff was going on in the ivory towers of mathematics, and a lot of the notations used were very convoluted and difficult. It wasn't very accessible. Then in the mid-1960s, predicate logic was made far more elegant and accessible and easier to understand by two professors at UCLA, Donald Kalish and Richard Montague. And I was very fortunate to be a student of Don Kalish. He was my favorite professor at UCLA. Now, our mathematical theory that we're going to use in these videos is built on first-order predicate logic. It's completely rigorous. We will mechanically check each proof as we go, and we're going to use a variant of Kalish and Montague's proof method. And for those of you who are mathematicians, just so you know, we're not going to use set theory. We're going to use predicate logic without the set theory. So now, looking at our diagram here, I've made bright pink with a yellow around it, yellow box around it. It says videos 2 through 5. This is in part of what we're doing now. And what I'm going to do now is I'm going to give you glimpses of videos 2 through 5. In other words, we're going to see, okay, so videos 2 through 5 over here on the left side of the diagram. This is when I'm teaching you the logic. Let's take a peek at each one of those videos. Okay, video 2, the crash course in geometry proofs. Here's what's going to happen in that video. We're going to use diagrams like this. We're going to talk about points and segments and angles and triangles. And we're going to do proofs. And here's one of the proofs we're going to do. See, we got some givens. We're proving something. It's a diagram. And here's the proof. And you know what? You watch that video and you will understand all of this. I'm going to take you through it step by step by step. And by the time we get to the bottom of this proof, you're going to go, wow, I get it. I understand. It all makes sense. It's beautiful. And that's what it is. And let me teach you, and you will see it. Then in video 3, we're going to talk about sentential logic. Let's take a peek at that. We're going to use capital letters P, Q, and R to mean whole sentences. For instance, capital P might mean Tom loves Sue, and Q might mean capital Q, Sue loves Alan. And we're going to use some symbols. We're going to use this symbol right here for not, this symbol for and, the symbol for or, the symbol for if then, and this symbol for if and only if. And then we're going to put the sentences like P and Q together using these symbols to make bigger sentences, like this. This sentence here, I've used the if then symbol. See, this means if then, the double arrow pointing to the right. So this sentence here means if P, then Q. Well, what do P and Q mean? The P, you can see it up here. You can look and see what this sentence is saying. It's saying, if Tom loves Sue, then Sue loves Alan. See that? We'll talk about this in video 3. And we're going to do proofs in video 3. Here's an example of a sentential logic proof done in the Kalish and Montague variant method. And I'm going to use color. The proofs are going to be in black and white like this. And I'm going to put color on top of this to show you how it all fits together. We're going to go through every bit of this, and by the time you get to go, oh yeah, I get it. It makes sense. So that's what's going to happen in video 3. All right. Now in videos 4 and 5, we're going to do predicate logic. Let's talk about that. Take a peek at that. Now, what is a predicate? I keep talking about predicate logic. What's a predicate? A predicate is the verb portion of a sentence with blanks for the nouns. And a predicate is not a sentence until the blanks get filled in. We're going to use capital letters for predicates, excluding P, Q, and R, and excluding G and H also. All the other capital letters can be predicates. So for instance, capital M. Let's say capital M might mean this. Might mean blank is a man. Now blank is a man is not a sentence until the blank gets filled in. And L might mean blank loves blank. Well, this has 2 blanks. Also, certain symbols can be predicates like the equal sign. Equal sign has 2 blanks. Blank equals blank. All right. So now using the same 2 sentences, predicates, M and L, now we're going to use lowercase letters A through Z to represent the nouns that go in the blanks. They're also variables. So for instance, lowercase c might mean Cindy, and lowercase d might mean Dan. Now to make a sentence, what we do is we plug variables, lowercase letters, in for each of the blanks. But what we put the predicate letter first, followed by the lowercase letters, 1 for each blank. For instance, right here, capital M, lowercase c, big M, little c. What does this mean? Well, the big M means blank is a man, and the little c means Cindy. So the Cindy goes into the blank. And so we get Cindy is a man. Okay, that's a sentence. I've never met a Cindy who was a man, so it's probably false, but anyway. All right, let's look at another one. Capital L, small d, small c. What does this mean? Well, the L means blank loves blank, and we're putting D and C into those blanks, so this means Dan loves Cindy. See that? We're also going to use some additional symbols in addition to the ones we already talked about in sentential logic. In predicate logic, we're going to have a backwards E, which means there exists, an upside down A, which means for all. The equal sign, well, you already know about that one. The backwards E with an exclamation point. This means there exists exactly one. Now this is about uniqueness, and I've taught you about uniqueness in this video already. We already talked about it. And then the candy cane means the. We also talked about the in this video. So I'm getting you ready, see? And then we're going to make sentences like this. This says, and I'm not going to cover this in detail. We'll cover this. This is a little bit trickier. This says, there exists something X such that X is a man and X loves Cindy. In other words, some man loves Cindy. We'll cover that in detail in video 4. And we're going to do proofs. The proofs in predicate logic. Here's a proof in predicate logic. We're going to do this proof. You can see the upside down A. You can see the capital letters and small letters. And we're going to just go through this, and you're going to understand every bit of it and go, yeah, it makes perfect sense. Okay, so here we are. We've just finished, I made cyan color this little tour of videos, videos 2 through 5. I have a little more to cover on our formal mathematics, which is the great power of a mathematical theory. And what is that great power? The great power is that by starting with obviously true statements, things that are obviously true, and applying logic, we can prove the truth of statements that are not obviously true. That's a big deal. Let's look at a famous example from geometry. Now, based on obviously true axioms, which I'm not going to talk about, we don't have time in this video, and applying logic, something that is not obvious can be proved about these 2 diagrams. Let's talk about these diagrams for a second. Each of these, I'm going to use a little pointer here to help me out, a little red pointer. Okay, each of these 2 diagrams has a triangle. The triangle is white, and then there are squares drawn on the 3 sides. Now let's look at the diagram on the left. The diagram on the left, there's an angle here where the blue and the green squares meet. That angle is a 90-degree angle. Okay? But in the triangle, in the diagram on the right, look at that blue square there. Can you see it's kind of tipped over a little bit? That's because the angle right here between the blue and the green is actually a little bit bigger than 90. So we have 90 degrees on this one and not 90 degrees on this one. Now here's what I'm going to tell you. You know about area. Area is in square inches and square feet, square meters, square centimeters. What is not obvious here is that in the diagram on the left, the area of the blue square plus the area of the green square precisely equals the yellow square. And in the diagram on the right, where the angle is not 90 degrees, the area of the blue square plus the area of the green square does not equal the area of the yellow square. In other words, whether or not that angle equals 90 or not determines whether or not the areas of these two smaller squares add up to the bigger square. Huh? Is that obvious? Can you see that by just adjusting that angle a little bit, it's going to determine whether or not the areas add up or not, or even if they... It's like, what? First time I saw this in the 7th grade, I was like, what? I don't believe that. I have a degree in mathematics and I still look at it and it's like, wow, that's amazing, because it's not obvious. Now, unfortunately, what happens in math classes all over the world is students miss the fact that this is not obvious. Instead, they're taught mechanical procedures for plugging numbers in. Let me show you how that works. You see, we can put letters on each of the three sides. The blue and the blue can be A, and the green side B, and the yellow side C. And again, in the other diagram, now granted the C in the other diagram is a little longer. And then we can figure out the area. The area of the squares would be the side times the side, so it would be like A squared, B squared, and C squared. These are the areas of the squares. And now we can write an equation down which says what we just said. And we can say on the one on the left, where the angle is 90 degrees, A squared plus B squared equals C squared. And in the one on the right, where the angle is not 90 degrees, A squared plus B squared does not equal C squared. This is not obvious. But what students are given is they're just taught, oh, this is the Pythagorean theorem. The diagram on the right is ignored. It's not shown. In fact, they're just shown this formula, A squared plus B squared equals C squared, and then given a bunch of numbers to crank in that formula. And the whole beauty and wonder and significance and magnificence of this magnificence just goes right over their head. They're just, oh, we learned the Pythagorean theorem. This is called the Pythagorean theorem. What's important here is to understand that the truth that this is not obvious, and the way we know it's true is by the logic, by applying logic to things that are obviously true. This is the great power of a mathematical theory. All right, now this is what we're going to do with the G-proof, because for a lot of people it is not obvious that God exists. So in videos 6 and 7 we're going to present 5 axioms that we think are obvious. And then in video 8 we're going to apply predicate logic to prove that there exists a unique, self-causing, omnipotent phenomenon. In other words, we're going to use formal mathematics as a window, predicate logic as a window. We're going to look through that window and see God. And how are we going to see God? By understanding the proof. Understanding the predicate logic and the proof. That is how we actually see God. Okay? And so here we are. We've finished now our discussion of formal mathematics. We're at, I've made that box cyan color now, which means we're done with that. And so now we're going to actually use formal mathematics when we talk about G-theory over here in just a moment. And we're also going to obviously use it in videos 6, 7, and 8. Okay, so now let's move on to the next section of this video, which is the introduction to G-theory. And so this is G-theory, formal mathematical theory, a formal mathematical theory of phenomena and causation. Here we are in the outline. This is where we are right here. So what we're doing is we're creating a mathematical theory with 3 inputs, a logic system, a list of undefined terms, and a list of axioms, and 2 outputs, a sequential list of defined terms and their definitions, a sequential list of theorems and their proofs. We don't need the system of calculations. That's why there are only 2 outputs. And now let's look. This is 5 things. Let's look where these 5 things are on our diagram. The logic system is over here, videos 3, 4, and 5, right? The undefined terms are here in video 6. The defined terms are here, also in video 6. The axioms I've got split between videos 6 and 7. And the theorems are down here in video 8. See how that works? That's how we're presenting the mathematical theory. All right, so now let's use, we're going to dive in and take we're going to do a tour of videos 6, 7, and 8 now, so that you can see, we're going to take a glimpse of each of these videos now. Okay, so let's begin with video, here they are, 6, 7, and 8, and start with videos 6 and 7. So we're going to talk about our 3 undefined terms in video 6. The first undefined term is phenomenon. A phenomenon is anything that exists or happens. And every variable in our theory is a phenomenon. Our second undefined term is a part of, and this is a predicate with 2 blanks. We use this little symbol, which is a square-shaped C, to mean is a part of it. And the blanks, every blank is filled in with a phenomenon. So the phenomenon on the left is a part of the phenomenon on the right. And our third undefined term is causes, and we use a special symbol for that. It also takes 2 blanks. We have this solid triangle that points to the right. It means the phenomenon in the left blank causes the phenomenon in the right blank. All right, now let's look at some examples of phenomenon. The number 23 is a phenomenon. The planet Jupiter is a phenomenon. Plant life. The chemical composition of vitamin C. George Washington's victory at Yorktown. Newton's second law of motion, which is F equals ma, or F equals dp dt. Let's look at some examples of is a part of. My right pinky is a part of my right hand. Antarctica is a part of the planet Earth. DNA is a part of all known living systems. The Origin of the Species by Darwin is a part of all books written before 2000. The Holy Bible is also a part of all books written before the year 2000. And let's look at some examples of causes. Now these examples are loose, and I will explain why they're loose later. We'll get much more careful about how we use the word causes when we get to video 6. This is just to give you a glimpse. Gravity causes apples to fall from a tree. An iceberg caused the sinking of the Titanic. The union of an egg and sperm causes pregnancy. The oscillation of electrons in a wire causes radio transmission. That's an antenna. Also in video 6, we'll talk about our first 3 defined terms. And they are all capital letters that take 1 blank. They're all predicates. Okay, that capital S is a predicate that means blank is self-caused, meaning it causes itself. The capital C is a predicate that means blank causes something. And the third definition, omnipotence, capital O, means blank causes everything. And these are the technical definitions right there, which we'll use and we'll talk about after we've talked about, been through all the predicate logic. All right. Here are our 5 axioms, which we're covering in videos 6 and 7. I'm not going to talk about them now, except for number 2. I'll just explain briefly. Axiom 2 is transitivity. It says if phenomenon R causes phenomenon S, and phenomenon S causes phenomenon T, then phenomenon R causes phenomenon T. Okay? That should be obvious. All right. So that, and now what we're going to do is look at video 8. What's going on in video 8? This is where we're going to do our formal, rigorous proofs that God exists. And here are we're going to prove 3 theorems T1, 2, and 3, and here they are. And look at theorem T3. It says, it has a backwards E with the exclamation point. What it actually says is, there exists exactly one phenomenon, G, lowercase g, which is self-caused and omnipotent. So that's what we're going to prove. We'll prove, and I'm going to show you the proofs right now. I'm going to flash them at you. I'm not expecting you to understand them at all. I just want you to see what's coming. Here is the proof of theorem T1, and we're going to go through this in detail in video 8. I'll use a lot of color, and we'll go right through the whole thing, so you'll understand it all. And okay, and then here's the proof of theorem T2. And by the way, if you look here on line 2 over on the right-hand side, see where it says T1? Because we're using T1 in the proof of T2. All right, and we'll go through this in great detail. You'll understand it all. And then here's the proof of theorem T3. And by the way, if you look in line 2, you see it says T2 there over on the right, because we're using T2 in the proof here. And so when we get done with all that, it will be done. We will have proved that God exists, and you will understand the whole thing by the time we get done with video 8. Okay, so that makes that finishes our glimpses of these 3 videos where we prove God exists, and that's why I made this cyan up here, videos 6 to 8. And so the next thing we're going to do is we're going to talk about a work in progress. Okay, here we are on the outline, work in progress. Look, we're almost done. We're talking about versions of G-theory. The G-proof is evolving. It is a work in progress. What we're doing here is we're using mathematics to discover and explore the existence and nature of God. This is profound. This is amazing, fascinating stuff. We're learning about God by looking at God through mathematics. Just as we learn about the universe by looking out at galaxies with a telescope. Mathematics is our telescope here. All right. Now, we presently have 2 versions of G-theory. In these 9 videos, we're presenting version 1 of G-theory. In some videos, I will talk briefly about version 2 of G-theory. Version 2 is more complicated. What we do in version 2 is we weaken axiom A4, and we add 5 new axioms that are all easy to justify, and we get what I think is a better result. On our website, thegproof.org, you can obtain copies of 2. We have a technical paper on version 1 and a technical paper on version 2. I'm hoping by the end of, if you get all the way through the 9 videos, that you'll be able to actually read that version 1 technical paper and go, yeah, I understand this. And if you can do that, maybe you can read the version 2 technical paper, although it's more complicated. All right. And as we develop G-theory and we create version 3, version 4, we'll put technical papers on the website for those versions as well. All right. So that takes care of our introduction to G-theory. There's only one thing left to do here, and that's to take a glimpse at video 9. So consequences of the proof. So here we are at the bottom of our outline. We're almost done. So we're going to look now at video 9. One of the things we'll do in video 9 is present a challenge to atheism. We'll talk about the challenge to atheism. You know, an atheist is not going to want, this is not going to be happy news for someone who wants to believe there is no God. And they may try to find ways to reject the G-proof. Well, they can either do it rationally or irrationally. We're going to talk about the rational. There are actually 4 possible ways to rationally reject the G-proof. And we're going to show that each of those methods requires supporting a highly unlikely scenario. And Occam's razor, which we'll talk about, supports the G-proof because it says this is silly to support something that's highly unlikely, just to cling to a theory that is unraveling. And then there are also many irrational strategies for rejecting the G-proof, but I'm hoping no honest atheist is irrational, but some might be. We're going to look at one of those examples right now. And that is, here's an example irrational strategy. Reject the G-proof based on things that have nothing to do with it. That's irrational. For instance, things about people whose great work this proof is based on, but they're unrelated to it. You know what? Gottlob Frege was anti-Semitic. And he actually supported Adolf Hitler. Ah, there! Frege supported Hitler, therefore his mathematics is no good, and the G-proof falls. Right? Nonsense. That's completely irrational. What about things about me that have nothing to do with the proof? You know, I've written a lot of things, I've put things on websites. One time I had a website that went viral. Tens of thousands of people saw it, and a lot of people reacted very positively to what I wrote, but the much larger number had negative reactions. They made fun of me, they ridiculed me, and they wrote all kinds of things. They took what I wrote and twisted it upside down and wrote false things and complete nonsense. And you know what? That if you go out and look up on the internet is littered with all this garbage that these people who have never even met me wrote about me. Now what you could do is you could look at what they've written and say, oh, there. Because these people who never met me, who know nothing about the G-proof, and are not very intelligent because you can tell that from reading what they write, therefore the G-proof must be no good, right? Well, that's pretty irrational. Or, some of the things I've written about are have to do with sex and prostitution. Ah, now we're getting to the nitty-gritty. This is how we can bring the G-proof down. Bring it down on a sex charge, right? Come on. You know, I actually believe that women, I believe in worshiping women sexually as goddesses. And I believe that prostitution should not only be legal, but it should also be honorable, and it should be a respectable career choice for a woman to make. And there, you know, there are a lot of people who agree with me on that, but most people don't. Ah, there we go. Mark Emerson believes that prostitution is a good thing, or it can be a good thing, therefore the G-proof falls. Right? The G-proof has nothing to do with sex. Or you could read on the internet about my legal battles, a lot of court cases, about one person I've had a lot of court cases with. So what? That has nothing to do with the G-proof. You know what? I'm just a teacher here. This proof is much bigger than me. This proof will survive me. This proof has to be looked at for itself, not based on anything about me personally or about Gottlob Frege or anybody else. All this personal stuff, it's irrelevant. What counts is the proof itself. Okay, I have some interesting questions to ask about atheism. Does rejecting the existence of God in the light of the G-proof require taking the non-existence of God on faith? Interesting question. Will atheism now become faith-based? Interesting question. Will believing there is no God become like believing that the earth is flat and motionless? Or that matter is continuous and has no atoms? Very interesting questions. We'll talk about them in video 9. And lastly, in video 9, we're going to talk about the impact that the G-proof has on several fields. Science must now develop in accordance with the monumental result that a unique, self-causing, omnipotent phenomenon exists. This is deep. Religion. Religion is also deeply impacted. You know, the problem of evil is now partially resolved. We'll talk about this in video 9. What's the problem of evil? Well, if God exists, and God loves us, and God is good, and God is omnipotent, then why does evil exist? You know, this has perplexed theologians for thousands of years. This drives many people to atheism. But we've now partially, not completely, we've partially resolved the problem of evil. Also, another one, this is very controversial, human free will does not exist. Choice is just an illusion. Choice is very popular today, but it's just an emotion. We'll talk about that. Very controversial. Now, lastly, public education, law, and government, in those fields, God cannot be excluded based on the separation of church and state. Why not? Because God falls squarely within the domain of mathematics and science, just like the multiplication table. Can you exclude the multiplication table from public education because it's part of the church? That's nonsense. God belongs to both church and state and every other field. And you know, there's this growing trend to just exclude God. Can't have anything to do with God in public education, public universities, government buildings. This has to change, because the separation of church and state has nothing to do with God. It has to do with those institutions, not God. God is beyond church and beyond state and part of both of them. Okay, so that's it. We finished with video 1. It's all cyan now. The next video is video 2, Crash Course in Geometry Proofs. I hope to see you there. Thank you very much for watching. I'm Mark Lawrence Donald Emerson.